Good afternoon, class. Now we're going to start lecture 18, Trajectory Planning Methods, Part 2. Last lecture, we have covered up to this section, up to graph-based methods, which is part of the introduction to robot path trajectory planning. And it contains many different methods, and we covered one of the major method, which is graph-based methods. And one thing I would like to emphasize is that in graph-based methods, we introduce you to graph construction and search algorithms, 2 bullet points, okay? But this graph-based methods does not necessarily, so let me put it this way. So we have these 4 sections within the this large bullet points part, but this does not necessarily mean each methods are completely different method, meaning that they do have intersecting regions, meaning that, for instance, sampling-based methods can also use graph construction concept or approach. And more importantly, search algorithms that we introduced in last lecture can also be applied to other methods, such as sampling-based methods. Okay, so these four methods are not completely independent. So that's what I wanted to emphasize. So sometimes they share some concepts, similar concepts, some don't, but their principles and idea are somewhat different. So let me emphasize that, and then let me move on to these 3 sections. So today, I'll probably be able to cover 2 sections: sampling-based methods and potential field methods. Sampling-based planning. So please recall last lecture, the graph construction and search algorithms. We use different graph construction methods, but many of them had these downsides. So let's go over this description. To get around the problem of trying to divide the region uniformly into small cells, one approach is to randomly sample locations in the space and try connect the samples. Often a larger portion of the working volume is space-based, so if 2 points are near each other, it is often the case that they can be connected by a simple path. The basic idea of sampling-based planning is abandon the concept of explicitly characterizing free configuration space and obstacle configuration space. A collision detection algorithm probes C to configuration space to see whether some configuration lies in free configuration space. So what this means is, prior method that we covered, we had to explicitly design and identify the free configuration space. So sometimes it's called roadmap, right? So we need a map, that graph map that we can apply search algorithms on top of it. But sometimes that's a lot of work, and sometimes that's not very efficient, because you need to first construct the entire graph before you start searching. Okay, and that can be quite inefficient. So here, so this is what we covered last time. So we talked about just simple grid approach when it comes to graph construction, and we also saw not necessarily identical grid-like cells, but more of a graph-based roadmaps. The problem is, like I said, how do we construct this graph? Well, so here are the motivations. The previous methods rely on explicit representation of the obstacles, and this can result in excessive computational burden. Avoiding such representation is the main underlying idea of sampling-based methods. And sampling-based methods rely on collision checking module. Okay, so you can sort of see. So like I said, sampling-based method can also be considered as a graph-based method. Can you guys see? So that's what I meant earlier. So it's not like graph-based method, sampling-based methods are two completely different methods, but sampling-based methods can be a graph-based methods. Okay. But sampling-based method is one type of graph-based method, and there are two traditional, conventional methods. One is probabilistic roadmaps, and the other one is rapidly exploring random trees. And a PRM and RRT. PRM, in simple description, PRM, you need to construct the roadmap, in random sense before you start search. Okay, so you're going to construct the roadmap before you start search. Whereas RRT does construct the roadmap as you go, meaning that online construction and search. So there's pros and cons, and we'll talk about that. So PRM, probabilistic roadmap, has two steps. Step one, build a roadmap by connecting nearby configurations using simple planners to construct a graph of valid path segments. Step two, query, meaning search the graph using a graph search technique. So here again, we can use Dijkstra, A star here. So again, things we covered last time it can also be applied to other methods. Okay. So here is more detailed steps to construct a roadmap. So you need to initialize an empty graph G. Vertices will correspond to configurations, edges to collision-free path, sample configurations, AI and C free. Use a metric defined in C space to compute neighborhood set of AI or action space of vertices Q already in G. Local planner, check if A of I can be connected to points Q. The neighborhood set, add to edge set if no collision detected, terminate when an edge is added to roadmap. So here's more descriptive illustrations. So what's gonna happen is initialize empty graph and C space, and you are going to sample random configurations in C space. So you're going to, sample these, in this case, position of the robots in the configuration space. And some will be in the free space, some will be in the obstacle space. And then you are going to remove, the nodes that are in the obstacle space, because obviously it's going to lead to collisions. So we have collision-free configurations, samples, and then we're going to create edges to nearest neighbors. So these are edges, right? And then we're going to do, we're going to check collision again. And we are left with these two edges. And we want to repeat this process for all sample nodes. And then we have graph constructed. And the probabilistic keyword comes in when you sample the position. Okay, so in prior work, prior method, it was deterministic. So someone has to, either computer, human, or automated method has to deterministically fix the nodes in the configuration space. But here it's done randomly. Okay, and you're going to apply, now you can apply all kinds of search method to start, and you have a goal, then you will find the optimal solution or near optimal solution. So primitives required, method to sample configurations in free C space, method to check for collisions in C space. Pros and cons are listed here. Pros, probabilistically complete, apply easily to high dimensional C space, fast query processing. Cons, don't work well for narrow passages, because let's say this obstacle was bigger, then if you don't have samples here, then it's highly likely that you won't find the path, meaning that this has collision, this has a collision, so no path through that narrow path. Okay, so when you have narrow passages, you need to make the sampling, you need to sample with higher density, okay, to make sure you get samples through the narrow passages. Okay, so that adds another design parameter or hyperparameter kind of thing. Hard to connect vertices for differential motion constraints. Hard to sample uniformly in configuration space. So now let's move on to RLT. This is sort of online approach of PRT, similar to PRT, PRM, but for single query problem, a tree may be enough. But again, this depending on the problem, how challenging the problem is, what the roadmap looks like. So the basic idea is build a tree by generating next states in the tree by executing random control. So here's the description. So let me explain using figures, okay? So what's going to happen is that you're going to start here. So instead of constructing the entire roadmap, like we did in PRM, we are going to create trees as we go. So we are going to select, we are going to sample these nodes, which is from decision-making point of view, a tree, right? And then we're going to create, continue making trees randomly, and we can hopefully get close, we can hopefully find the path to the goal, okay? The random part comes in when we sample the nodes, and it emphasizes exploring part, rapidly exploring part, because we sample as we go. So this way, it's faster. It may be more efficient in some environments than the PRM. But if you have, but it probably loses optimality when compared to when you have the entire roadmap. So depending on the problem, right? Depending on the cost function, and you may have to detour sometimes. You may have to go through narrow passages, but if you do everything online, then there is a chance that, oh, you move this way, and then you find that it's blocked, right? And then you made a mistake, and that's a pretty big penalty, right? But when you do this beforehand, then you can sort of see this, the big picture beforehand, and you can correct the roadmap if you have, different algorithms, collision checks, blah, 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 right? So there's pros and cons, which is listed here. Again, probabilistic complete, exponential rate of decay for probability of failure, asymptotically optimal, but for non-holonomic robots, generating edges to sample configurations requires solution to the two-point boundary value problem. So far, we connect vertices, nodes, with a linear local planner. But in reality, we have many robots are non-holonomic, so we need to create path for non-holonomic robots vehicles. So in that case, there are different techniques. We can do, filtering. We can do fitting, polynomial fitting. Different methods are available. And here's one example. So here they have constraints, kinematics, dynamics, that cannot be integrated into positional constraints. The kind of different constraints that appear in planning dependent not only on the system but also on how the task is decomposed. Non-holonomic planning is typically used for problems with kinematics constraints only. So for instance, so we can combine, so we introduce you to RRT, right? Rapidly exploring random tree. But what if your robot was non-holonomic robot or vehicle? Then you might want to consider using local planner connecting these vertices instead of a linear local planar. So here, everything was simple linear line, but we could use polynomial, for example, to create smooth path around the environment. So this is one example of using RLT with say polynomial local path planner applied. So again, I'd like to emphasize that many of the contents, many of the methods I am introducing here in this lecture notes are not independent methods. You can mix and match almost. So that creates a lot of so different methods are suitable for different problems. And for different problems, you may need to come up with method that's combination of different methods. Okay. And this is also closely related with your how you formulate the problem and how you define your configuration space. Okay. And let's move on to potential field methods. This one is a bit different from the graph-based methods we talked about so far. Here, potential field methods, there's no explicit roadmap. Instead, construct a real valued potential function over the space. We are going to introduce attractive potential, UA, and then repulsive potential, UR. And obviously, attractive potential should lead the robots or the space towards the goal. Okay, so the goal has lower potential, and the starting point should have higher potential. So hopefully, if you sort of put, say, a ball on top of this space potential field, then the ball is going to flow through the to the goal. Okay, that's the main idea. But of course, there's obstacles in the space, so you should introduce repulsive potential so that the ball can avoid the obstacles, and this repulsive potential needs to do that job. Okay, and differentiate potential will be gradient U, and then we can use gradient descent method, which is used in many optimization problems. So I don't have to go through this again, right? So we talked about optimization problem, right? So this is more like a real-time optimization method in the space. So we need to create correct good potential field so that the robot can flow through the space to the goal. Okay. Here's more detailed description. So I basically summarized what the potential field method is. Here's more detailed description of that. So this is an obstacle, and you're going to apply a repulsive field around, so that your robot will not collide, will avoid the obstacle. And eventually to the goal. So I'm trying to determine whether I should go line by line or sort of go fast here. All right, let me go fast. Okay, I don't think this is too very new to you guys, right? All right. So potential field methods, I think it's very intuitive. Like I explained, we create this energy field with high energy, low energy, and then after we construct this potential field, we can compute the gradient, and then that gradient tells you which direction to go, and the robot will follow that direction. So here's attractive potential, repulsive potential, and that's going to get you close to goal while avoiding obstacles. So the main thing here is constructing the potential field, okay? Designing the potential field. That's engineer's job, and that's the only thing you need to do. Everything else, the computing gradient, following, executing the motion is almost all deterministic. Everything is done automatically. So it's all about designing potential field. Okay. And here's how you can, these are examples, okay? How you can design repulsive potential, how you can design attractive potential. I mean, obviously one simplest way to design attractive potential is, current position being highest, goal being lowest, but what about somewhere in between, right? You may have some freedom, right? So these are other examples. So here is attractive. So here is configuration space. And this is sample attractive potential. And then repulsive potential. So summation of those two will create these potential field. And then if you use gradient method, it's going to flow through this passage between the two obstacles. Okay. This describes gradient descent method, which I think we talked about multiple times. But this is not perfect. We talked about local minimum, global minimum, right? Gradient method is effective when it comes to, if you're looking for local minimum, meaning that if you have convex problem, and if you're looking for local minimum, then this will do the job. But if you have very complicated field with multiple local minima, you may not be able to find the global minimum, right? So that needs to be understood and taken considered. And there are different techniques to avoid these limitations or mitigate these disadvantages, but this is the main idea. Okay. So here's more. Okay, here's the pros and cons. Okay. Computationally efficient. This is also this as soon as you determine how you're going to design the potential field, then you're good to go. All you have to do is compute gradient and apply that, apply for motion planning. More than just one path is possible, but downside would be local minima. It can fall into local minima. Representation of C space is hard in high dimensions. Let's say you have 3-dimension space. How are you going to design it? Or, you know, four dimension. For instance, in this example, this is a good illustration of this local minima. So if you simply design attractive field with start position to goal with flat, say attractive field, so it robot is directed or attracted to the goal, but then there's an obstacle that looks something like this. And what's going to happen is the robot is going to fall into this local minimum and get stuck there. Okay, robot will not be able to find this path, right? But if you did graph construction beforehand, and then look at the big picture, the entire picture, and then search the path, then you would be able to avoid these type of obstacles, right? So this is downside of sort of real-time online search algorithms, okay? So here's more information about potential field methods. If you're interested, you can take a closer look. But I think that should give you, pretty good idea of what potential field is about. Okay. I will for today I will stop here and continue from collision avoidance in the next lecture.